Assalamu alaikum. Sedimentology, Part 1 Weathering and Sedimentary Cycle. Presented by Khalid Amrouni, PhD in Geology, Texas A&M University. Khalid Amrouni is a staff member at the Department of Earth Sciences, Yunus University, Benghazi, Barga State, or Cyrenaica State. References use it, Applied Sedimentology, and Essentials of Geology. This is the Earth Sciences Department at Yunus University, and this is the main entrance of Yunus University. This is the Prince of Cyrenaica, Idris Sunusi, and this is the flag of Cyrenaica State behind the Prince Idris, and this is Benghazi city, the capital of Cyrenaica. This is Omar al-Mukhtar, the chief commander of this Sunusi family, and this is the map of Barga State or Cyrenaica State. Outlines of this talk. First item is introduction, and then sedimentary cycle, and then weathering. Introduction. The genesis of sediment particles. So here we're going to study the origin of sediment particles. A sedimentary rock is the product of a provenance and a process. Provenance is pre-existing rock, and process, weathering mainly. The sedimentary cycle it's made up of weathering, erosion, transportation, deposition, lithification, uplifting, and weathering again. Transportation and erosion, they share these agents: wind, water, glacier, and gravity. Lithification consists of two parts: compaction and cementation. And the third part is weathering. We have three types of weathering: physical, chemical, biological. And biological was associated with the soil formation. The sedimentary cycle. So the pre-existing rocks, or the province of pre-existing rocks, will be subjected to weathering, and weathering mainly is the process of disintegration and decomposition of rock materials in situ. No transportation, in situ. And then the second step is erosion. After the rock became more like disconnected particles due to weathering, the erosion comes to do transportation and incorporation of these sediment particles and then transport them. So the four agents of erosion and transportation, they are wind, water, glacier, and gravity. And then after the transportation, the sediments will be deposited either in lakes, in rivers, channels, in the sea. And then what happens to the sediment? They'll be lithified. That means cemented and compacted. Now they became rocks. And then these rocks will be uplifted and exposed to the surface to be subjected to the weathering process again, and the process will keep going on and on and on. So for example, this turbidite sequence of the Upper Cretaceous in Cyrenaica, this is called Lathroon Formation, is made up of turbidite deposits, Boma sequences, had been through a full sedimentary cycle. Its particles had been weathered, eroded, transported to the ocean, and then deposited on the slopes, under the sea, under the ocean, under the water, the ocean water, and then lithified, compacted and cemented, and then uplifted. And now it's uplifted and subjected to a new cycle of weathering. So these white packages here are just turbidite sequence. The top here is the weathered surface is quaternary deposits, and this and can you see when you see those fractures prove the process of lifting tectonics. So weathering, physical, chemical, biological. What's the physical weathering? Mechanical disaggregation for rocks. Chemical, two processes, oxidization and dissolution of a rock mineral. Biological, caused by mechanical and physical effects of organic processes on rock. So organic processes will cause chemical and physical effects on the rock. Erosion, four agents, and subsequent transportation. So transportation, erosion, they share those four agents: gravity, glacial, running water, and wind. Running water. So here, those four pictures for the four agents. This is wind transportation, and the picture, by the way, the Sahara in the southern part of Libya. And here, this is the wind transportation. It's very selective. And this water transportation in this picture from Cyrenaica state, northeast Libya. And glacial, the third agent. And the fourth agent is gravity, and we see landslide here, or slump, sorry, apologize, see slump. This is a gravity effect. Now the products of weathering, it's very important, are twofold. Weathering products, residual, which is particles, solutes with solution. Particles, that means the grains. And the product of the weathering process is either particles, grains, and the grains, they range in size from clay size up to boulder size. And soluble fraction of rocks carried in water could be sodium, potassium, calcium, magnesium. All of these will be carried in solution. So how it works? So we have larger particles like large sand grains, very coarse sand grains, and gravel size will be transported by rolling. The sand grains in fine and very fine, medium, sometimes coarse, depends on the current, will be transported by bouncing and saltation. Silt size and clay size will be suspended. Plus, ions will be dissolved in the solution. So suspension, we have silt clay size plus dissolved ions. This figure is the same, this one is colored. So transporting media efficiency. What do we mean by efficiency here? The ability of the media to handle and segregate the products of weathering, which is the grains in the solution. How to handle them? To segregate them to the main classes of conglomerate, sand, shale, and limestones by natural process. So wind action, is it efficient? Yes, the most selective transporting agent of all. Maximum size 0.3 millimeter that the wind can carry, and that's medium to coarse, medium to fine sand grain size. So medium to fine grade sand. So from silt, clay to medium fine sand size. And then running water, efficient carrying material in solution, dissolving material. Less efficient transporting residual sediments. So running water segregates sands from gravel and clay from the brittle sand. So we'll give us sandstones, the end product after sand will be sandstones. The calcium that carried in the water will give us limestone, calcium carbonate, and mud stone coming from the salt and clay. Glacier and gravity inefficient, very inefficient in agents of sediment segregation. Why? Because their products are poorly sorted from boulder beds and gravel and sand size. So they're all mixed. Was not able to separate sand from mud from gravel. They're all together in one rock deposit. Weathering. What's weathering? Includes the processes which break down rocks at the Earth's surface to produce discrete sediment particles. So then the product of weathering to produce discrete sediment particles. So decompose and break down the rock into smaller discrete particles. So the first type of weathering, physical weathering, we call it rock mechanical fracturing, and there are four types of it. Freeze and thaw, that happens in polar regions. Second one, insulation, happens in deserts where hot arid climate with large diurnal temperature ranges. And then the third type of physical weathering, hydration and dehydration. So formation strength will break down, especially if you have shale, clay minerals during wet and dry seasons. And the fourth type is stress release, especially brittle rocks like igneous rocks. So let's look at the freeze and thaw. Freeze and thaw happens in polar regions where water percolates through fractures, and then the water frozen became ice will expand. And that will enlarge fractures and break down the rock, like this example here and this example here. That's type of physical weathering. The second type is insulation, as we said, happens in the desert where the rock exposed to like wide range of temperature. During the day the temperature goes up to like 45-50 degrees, during the night freezing point below zero. The rock is made up of minerals, and each mineral has different rate of expansion and contraction, and this process of expansion, differential expansion and contraction, will exert stress on the rock, and that stress is enough and sufficient to create cracks and break down the rock into smaller pieces. Hydration and dehydration. So we said it's a formation strength breakdown when shale or clay minerals subjected to seasonal alternation between wet and dry seasons. So during wet seasons, some shales will expand and cause landslides. The dry seasons, that shale will dry out, shrink, and create shrinkage cracks. Stress release, this happened to igneous rocks. We call them brittle rocks. Overburden pressure released, so and rock expand and fracture. So fractures enlarged by chemical weathering. Let's look at this. So we have this igneous rock was under thick sedimentary package. When these sedimentary packages eroded, withered and eroded, so the pressure released above, the overburden pressure is taken away. The this igneous rock just expanded and crack it and foliate it, and then create these sheets, and then the chemical weathering enhanced these fractures and enlarged them. So this is the stress release. Now the second type of weathering, chemical weathering. Rock destruction by solution. The main agent is water. So the main chemical reactions involved in the chemical weathering are oxidation and hydrolysis. So let's look at the chemical reaction. Here we have H2O water, rainwater, will react with the CO2 from the atmosphere. That will produce bicarbonic acid. It's low pH acid, very weak acid, and that means that water that precipitated down on the ground becomes groundwater is acidic, and this bicarbonate can transform into carbonic acid plus hydrogen ion. So the released hydrogen ion may then liberate alkali and alkali earth elements from complex minerals. So what's the weathering, the chemical weathering products constituents? There are solutes, solutions, newly formed minerals, and residuum particles. So what's the solutes? Alkali metals, sodium, potassium, magnesium, calcium, strontium will be carried in water to the sea, to the ocean, and later will precipitate as limestones, which is made of calcium carbonate, dolomite, which is made of calcium magnesium carbonate, and evaporite, which is hydrous calcium sulfate. And newly formed minerals, they're basically clay minerals, hydrous aluminum silicate, complex group of hydrous aluminum silicate. Residuum or residual hard particles, usually silic and aluminum, based on the degree of weathering. But if you have mechanical weathering, no chemical weathering, just mechanical weathering, you get feldspar or mica. But if you have chemical weathering, you intense chemical weathering, your end product will be silic and aluminum residual. Okay, let's look at the chemical solution. This is these karstic features created in the limestone during this, due to the solution. So the chemical weathering is basically the reverse of Bohn's reaction series. So we have mafic minerals and feldspars. Simultaneously, they'll go through the chemical weathering, and the top part of the or the members at the top part of the Bohn's reaction series, like olivine and anorthite, those the first ones to be chemically weathered. And as you go down, these minerals like quartz is very resistant to the chemical weathering and might end up being residual products. So if we look at the mafic elements of Bohn's reaction series will be olivine, pyroxene, uh, amphibole, and biotite. And the feldspar side will be calcium feldspar, which is calcium plagioclase, sodium plagioclase, and potassium, which is orthoclase feldspar. And the two at the bottom of the Bohn's reaction series, muscovite and quartz. Quartz is very resistant. Here we have halite, gypsum, limonite, hematite, and calcite. Halite coming from calcium's sodium chloride, which is sodium is a solution in the water. Gypsum, hydrous calcium sulfate, calcium is solution, carried that solution in the water. And calcite, calcium carbonate, and calcium again carried in the water as solution and precipitated in the ocean. Limonite, hematite, just iron oxides. So the third type of weathering is the biological weathering, which is mainly organic process. How it happens, we have biochemical solutions, A, and B, we have physical fraction. The biochemical solutions due to bacterial action and humic acid. Humic acid is coming from the decayed organic material. the top part of the soil. And then physical fraction by plant roots. Soil is made up of debris and humus. Soil study is called pedology. Soil profile has zone A, zone B, zone C. Zone A, alluvial horizon, organic rich. So we have chemical, biochemical process. That means we have oxidization process and leaching process. Zone B, alluvial horizon. It's clay entrapment and precipitation. So clay deposits in this zone and will prevent liquids to come under to zone C. That's why zone C is physical weathering zone. Physical weathering dominates there. And then under zone C, unaltered bedrock, the lower zone of the soil profile. So the soil profile thickness depends on erosion rate, in the best case for to have higher or thicker soil profile, to have low profile in the area of erosion of weathering. Climate region, in the best climate to have thick soil profile, humid tropical climate with 100 millimeter of rain. Bedrock composition, the best bedrock to have thick profile is mainly basaltic. So note possible formation of porosity by weathering at unconformities. Yep. So biological weathering, we see here the tree roots breaking the rocks, and we see here some organisms living on the rock to create the humic acid. So the next one is soil profile. As we said, has zone A, zone B, zone C, and unaltered rock or bedrock. Zone A, oxidization and leaching, has a lot of organic material. Zone B, entrapment of a clay, so prevent anything to come down almost or minimum liquid will come down below zone B because clay. And then zone C is physical weathering. So chemical weathering is just zone A. Zone and behind physical weathering zone is just unaltered bedrock. So soils, climate affects weathering, and weathering affects the product or sediments product in a particular area. We have modern soils and fossil soils. What's modern soils? They basically depend on climate, rain, and temperature. So polar region, they have permafrost, no soil. And it's just no chemical weathering because there's no moisture and it's only physical weathering. So basically we don't have thick soil profile there. Climate, and the same thing for the desert. Desert zone, no soil, just only duricrust. We call it calcretes, silicretes, very thin, or ferricretes and evaporites. So no humidity, no moisture, no chemical weathering, only physical weathering. Also no leaching here due to capillary attraction. So fluids, they go up instead of leaching down in the desert. So desert, no soil. Polar region, no soil. On the other side, climate in the Arctic Circle, the temperate side, you will have chemical weathering. The same thing for tropical region. You will have chemical weathering because you have moisture and you have thick soils, and you have chemical weathering. And those thick soils will have horizon A, horizon B, and organic rich material. And especially in the tropical area, because you have humid tropical climate, very rich in iron, plus kaolinite, which is ferruginous soil, we call it laterite. So this is about the modern soils. The fossil soils, we call them paleosols, occur beneath the unconformities in the geological record. So soils, and that's evidence of subaerial exposure of the deposition environment. That's why we study soils, because they tell us about the unconformities, and the unconformities are very important surfaces to tell us their rocks old below the unconformities or older, and their rocks younger above the unconformity. And also unconformities are very important in the oil industry because they can work as conduits to transfer oil and gas, or they can work as seals to stop the seeps of oil and gas, petroleum products. So, what types of fossil soils or paleosols? We have earth seeds and we have cornstones, both fossil soils. Earth seeds carbonized plant roots in bleached white sandstones, usually in the fluvial deltaic. So you have bleached white sandstones. Above it, you find carbonized plant roots. And then cornstone caliche fossils or caliche fossil soil horizon. So mainly it's calcium carbonate, caliche. Happens in the fluvial in the old red stones. So carbonate one we call cornerstone, the carbon one or plant roots, carbonized plant roots we call earth seeds. So let's look here at the this diagram profile of modern hemisphere showing the relationship between climate, soil, and weather. So here we have precipitation in centimeters from 0 to 30, here temperature from 0 to 20, and here we have the altitude from tropical, from 0 the to tropical Cancer to Arctic Circle to 90 degrees polar region. And as we look here, we have this gray unaltered bedrock, gray, this hashed area is physical weathering, this black area is chemical weathering, that means soil. So at the polar region, almost no soil, just physical weathering because there's no humidity, just mechanical weathering. Arc is the same thing in the desert, no soil profiles, just physical weathering. But the black regions here under Arctic Circle and under the tropical area, they have thick soil profiles. That means you have horizons of the soil A and B, and you have chemical weathering active. Here we look. This is modern soils. This is the fossil soils. This is the earth seed, which is coal under it, plant roots carbonized inside, penetrating leached sandstone or bleached sandstone, very white sandstone. The same thing here. This is the cornerstone, which is caliche soil horizon. And here we have desiccation cracks, another indication of subair exposure and conformity. And here we have reworked caliche glassine channel floor. Now, clay minerals, classified according to the way in which hydrated aluminum silicate combines with calcium, sodium, magnesium, and iron. So, in the early stage of chemical weathering, simultaneously mafic and feldspar, those are the two arms of the Bones reaction series. The mafic ones that rich in iron, magnesium, they are chemically weathered. At the same time, feldspar side, which is calcium rich and sodium rich and then potassium rich. The mafic, which is olivine, pyroxene, amphibole, they produce chlorite clays, which is rich in iron and magnesium. Feldspars will produce smectite, a light kaolinite. Smectite, rich in calcium and magnesium, a light rich in potassium, kaolinite, hydrous aluminum silicate, pure. If the chemical weathering, the intense chemical weathering persist in progress in a warm, humid climate with a slow rate of erosion, magnesium, calcium, and iron will be flushed out and leached out of the rock and for these minerals and create quartzes and newly formed minerals. Quartzes, which is SiO2, silica. Newly formed minerals will be kaolin, kaolinite. This is a pure clay minerals. That means hydrous aluminum silicate. Bauxite is hydrous aluminum oxide. So there's no silicate with it, just aluminum oxide. So that means the silica is taken away from the kaolinite and just left with aluminum and water, aluminum oxide and water. That means this is bauxite. And we have also iron is limonite, hydrated iron oxide. So this is the chemical weathering, the intensity go in this way, and these the products. Clay minerals, again. We have three main types of residual deposits. So now we're talking about residual deposits. Are generally recognized and defined according to their mineralogy. We have laterite, kaolinite, bauxite. So what's laterite? Hydrous aluminum silicate with iron. The parent usually basaltic rock in a humid tropical climate. Kaolinite, we call it China clay. It's hydrous aluminum silicate without iron. The parent rock usually shale, granite, which is acidic igneous. Bauxite is hydrous aluminum oxide. So no silica, no iron. And this formed by the hydrogenesis of minerals, principally kaolinite. Limonite is another product. It's not important. It's hydrated iron oxide. And by the way, the bauxite ores, the bauxite is hydrous aluminum oxide, but the ores you find iron oxides and titanium oxides with it. This is laterite. This is China clay, which is hydrous aluminum silicate, and this is bauxite, which is hydrous aluminum oxide. This is hydrous aluminum silicate with iron, red. So clay minerals and chemical weathering intensity. If you have laterite, which is hydrous aluminum silicate with iron, with the increase of the chemical weathering, iron will be removed, and you will end up with just hydrous aluminum silicate without iron. And that's why we call it kaolinite or China clay. If the intensity of the chemical weathering increased or in progress, the silica will be taken away, removed, and you will end up with aluminum oxide and water, which is hydrous aluminum oxide, we call bauxite. Now, we studied the weathering process, and we knew the end product of this weathering process, particles and solution. And all of these weathered particles and elements will be transported, eroded and transported through four agents: water, glacial, wind, and gravity. So when these elements transported through water and dropped or deposited in the ocean, we'll have the end product here, limestone rock, which is made up of calcium carbonate, or chert, which is made up of silicate, pure silica. Or we'll get gypsum, which is hydrous calcium sulfate. This gypsum evaporate from the Miocene of Cyrenaica, Masiklo area, and this limestone with the chernobyls from Jebel Akhtar area, you see in Asia. Still in the chemical solutions, when they're lost in the ocean, will precipitate as halite salt in Karkora area in Cyrenaica. This is very recent. These sedimentary outcrops of Cyrenaica. And On the other side, particles, the grains, when they are deposited, for example, this one deposited along, it shows graded bedding, fluvial terraces, recent in Wadi Zaza area, and the grains, boulder, the gravel size grains decrease in size as you go upward, and then another cycle started. So there are like one, and here two, and here three main cycles. And there's another product, which is this course, the finer sand. This is a gravel, and this is sand size here. This bed is sand transported as grains and deposited, and above it shale, green shale here. This layer, green shale transported and deposited, so, transported suspension and deposited, shale deposit, and these two layers topped by carbonate rocks, the white one. And this outcrop basically in Cyrenaica, in Cyrenaica State, Wadi Bab area. And this outcrop, as you said, it's in Wadi Zaza area in Jabal al-Khadar. It was very close to Persis area. And by this, we came to the end of this talk, the take-home message. We had introduction to the sediments, the genesis, origin of the sediments, and then sedimentary cycle, and then we went in details through the weathering processes. And by this, we'll have 3 minutes rest to listen to the national anthem of Cyrenaica. Thank you very much.